Okay, excuse me, look up. Okay, the blue is homework tonight. The blue is tonight's homework. This is the last homework assignment for the first unit. I don't like to keep giving homework close to the test. I like to give a good amount of time to make sure you solidify what you've learned for the unit. Okay, so the homework has the answers on the back. Just make sure you're using the answers effectively. I may have mentioned this before. In college, for many classes, you can buy a solution manual from like Amazon. Solution manual is a full book that will have every homework problem worked out in detail with comments and explanations, because in my opinion, a good professor understands that that can be a very valuable resource to help you understand the material as long as you use it correctly. Same with this. If you use the answers correctly to just verify that your understanding is right, very helpful. Just don't use them incorrectly. It actually makes learning worse. So, this one is a practice test. It's labeled as such. No answers on this one. And this is in the exact format as the real test. So the real test will be 25 multiple choice questions just like this. Well, not just like these questions, but 25 of them. You have to finish the test within the class period. So basically have an hour and 20 minutes to finish. So this will give you a sense of the timing required as well. You'll fill out a Scantron, just like this. Okay. I didn't give you answers on this one because you want to treat this as much like a test as you can. So you don't want to do this with other people the first time. You want to do it on your own so you can figure out, okay, how am I doing? Somebody asked last period, should you study beforehand? Yeah, because you want to treat this like a test. Like, do everything you can, study, prepare, then see how you did. Okay, we will, we'll officially probably discuss this in class on Monday, but I have a second practice test I want to give you, which I'll give you next period. So really the best plan is to get a little bit ahead of the class. And then I'll be having some before and after school kind of help sessions to discuss this as well. So if you get this done earlier, you can come be a part of those sessions to help you prepare. So I'll give you 2 full practice tests prior to the actual test, which is on Wednesday. Okay? As the disclosure said, tests are worth 80% in this class, and because it's the AP test we're preparing for, I can't give you little tiny unit tests. It won't help. I've got to give you big chunks so you can learn to get it all together, since the AP test is cumulative. So this is the only test we have in term 1, and that's not really that uncommon. So this one test is 80%. So that's why I'm giving you 2 full practice tests in a week and a day to help you fully get ready for that test. So, questions? Perfect. This will count as a quiz. So we'll put this in Skyward as a quiz score. Yeah, please.
Do you need that by next time? Or
No,
you just
so
recommended it, but it's okay if we...
Yeah, official time will be Monday,
Okay.
when this will be officially due, as far as actually putting a score in Skyward. But it is to your advantage to do it quicker. And if you get it done quicker, you can come have me scan it and I'll scan it for you. So you can see how you did it. Questions? Awesome. Okay, I think I said this before. In a college level class, you should not come to class and then kind of shuffle through your papers and go, I know I have a question somewhere. You come to class prepared to ask specific questions from the homework if you have questions. So did anyone come prepared with specific questions?
Go over 30, just how to figure out the graphs.
So 30. Okay, I'm going to make a bunch of mistakes to start out with to illustrate kind of what would normally happen, honestly. Please speak up at any point in this discussion. This problem, if you understand this one, you'll be able to solve a good number on the test. Like just this one problem is a really good representation of key ideas that you must understand and memorize. So they give 3 different graphs. They say one is F prime, and one is F double prime, and you just have to figure it out. So if it were me, I would just start by saying, let's assume this is F. And so then, I follow F, I get to here, I would see a tangent slope that is equal to 0. But the trouble is, immediately I see a problem. Because the other 2 graphs do not have y coordinates that are equal to 0 at that same spot. So there's no possible way this can be F. You want me to talk more about that? Cool. Let's try again. Perhaps this is F. So this one's making some more sense. These 2 might line up. Tangent slope equal to 0 on F, causing a y coordinate to equal 0 on F prime. So that might work. Over here it looks similar. So far so good. Question? Cool. But second possibility is this. Maybe this is F prime. This is F double prime. Because the relationship is the same. Okay, cool. Let's keep going. Let's see if this is F and this is F prime. When F is increasing over here, so F is increasing, F prime would have to have positive y coordinates, so that's a match. When F is decreasing, I'm on the wrong graph, hold on, back up. So F is decreasing here. F prime would have to have negative y coordinates, those match. You want me to talk more about that so far? Cool. Let's see, when F is increasing again, F prime would have to have positive. So that's all working, but again, that still could be F prime and F double prime. Perhaps it would be wise to see if this is F double prime. So let's see. When F is concave down, so F is concave down here. Here's F being concave down. The F prime, F double prime, here's a problem. Here's F double prime being positive, which is wrong. When F is concave down, F double prime has to be negative. So this can't be F. Like these 2 would work, but that doesn't work to make those 3. So it's kind of looking like F prime F, and it looks like this would have to be F here then. Because I already know those 2 look like they're working. And I would just keep checking like that. I can keep going if you want me to. It's up to you guys. So, you want me to keep talking about it or just wait? Okay, cool. Elijah, you good? Who else bring a question to class?
32.
32. 32 says, the table gives selected values. Circle those two words, please. You're getting ready for a test in a week and a day. I can guarantee you there is at least one, and I'm pretty sure more than one question on the test where you have to understand that whenever you look at a table, you only see selected values. So I can see the value of the velocity at time equals 0, and I can see the value of the velocity at time equal 1. But the velocity at time equal 0.5, I have no idea. At velocity time equal 0.2, I have no idea. So you only see 5 points when in reality there's an infinite number. So don't make the assumption. So let's see, let's check the whole room. So how many are used to doing the following? You have a function, you have a formula, you make a table, and then you plot like 2, 3, 4 points, and then you just kind of gently connect the dots. Raise your hand if this is a very familiar process. Point? Okay. In calculus, they do things to kind of get you to forget. Well, that's just not always true. Sometimes they do connect smoothly. They don't have to connect smoothly. And you'll do far better in this class to never assume that they connect smoothly. This point right here, 0, -1, right there. 1, 2, right there. 2, 3, 3, 0. So those are the dots in purple that are in the table. If we connect them nice and smoothly, we get this graph, which means this appears to be the graph of the velocity. Okay? It's not. Well, it could be, I suppose. It's not the right answer because they want us to find the graph of the position. But the actual velocity graph could really do this. Okay? So don't assume you know what's going on in between. And I can show you AP calculus problems where you had to remember this. So they say selected values, I think, every time they give you a table. Don't forget it's selected values. Question? Awesome. Keep reading. So the velocity is shown of a particle moving along the x-axis. So right there, a picture would help. So here's an x-axis. Here's the origin of the x-axis. Particle moves along this. Okay? At time equals 0, the particle is at the origin. So that means this. Time equals 0. So this sentence right there, that purple sentence means exactly the same thing as that drawing. Question? Cool. Once we have this information, we could actually make a table if we chose to. We could say, here's time. Oops, that's a bad color. Let's go this one. We could say time and position. And we would say at time equals 0, the position is also 0. We can make a graph. We could say, if we take this table and graph the table, our graph would look like this. It's a position graph. And at time equals 0, the position is 0, so there'd be a dot right there. Okay, so please, memorize, make sense of, ask questions if it doesn't make sense. I've got 1, 2, 3, 4 different ways of representing information. And all 4 of them mean the exact same thing. So the purple sentence, this drawing, this table, this graph, they all mean the same. Anybody need help understanding those 4 things? Cool. I'm supposed to figure out which of the following could be a graph of the position. So looking at my graph of the position, I can immediately eliminate these 2. I want to talk about that. Because they told me the position of the particle was at the origin when time is 0. That means this, which means if I place this on a graph of position, I would have a dot at 0, 0. And these two do not have that. They have a dot at 0, -1. So those cannot be the graph of the position. Question? Awesome. Okay, the only clues I have left are this graph, this table has to match up with these graphs somehow. So now you have to remember how velocity and position are related. So raise your hand if you remember how velocity relates to position. Everybody? How is velocity related to position? And if you don't remember, talk to somebody, get it remembered. Test in a week. So how is velocity related to position?
At the point where it's time is that.
So hands up, hands, show me. Who knows? How is velocity related to position? Show me your hand. Let's go, Sarai. Nice. So right here, time equals 0. The tangent slope of the position graph has to be -1. How many knew that? Show me. 2 points. So if I look here, if time equals 0, that tangent slope is in no way -1. So I know that cannot be the correct position graph. You need me to talk more about that.
Can you just say that again?
So I'll get you to kind of say it as we talk, and then it usually stays in your memory better.
Mm-hmm.
So these two numbers are telling me that if I had a graph of velocity, there would be a point on the velocity graph at time equals 0, a y-coordinate of -1. So like this. Are you okay with that?
Yeah.
Good. But because velocity is the derivative of position, it also means that if I look on the position graph at time equals 0, I should find a tangent slope value that is also -1.
Oh, so it needs to be going negative?
Right. So
Okay.
this tangent slope is some positive number.
Okay.
So I don't know what number it is, but I know it's not -1.
Okay.
Does that make sense?
Yeah, that makes
2
sense.
points. Anybody else? So here, Rachel, don't really know exactly what that slope is, but it certainly is negative.
Mhm.
So I'm on the right path. This is a copy of that table. So I'm like, okay, got it. Times 0, slope -1. This one's something similar. Questions? I just keep checking. Time 1, the tangent slope should be 2. That's at least possible. This is not. That's still a little bit negative. So. Questions? Heather, please.
So the coordinates of the velocity graph, that's just the tangent, so like the y-coordinate, that's just,
Keep talking.
so like, if you look on the table, the coordinates, the y-coordinates of the velocity graph, that's just the tangent slope,
Of the position graph. Yeah, that's the correspondence. You see a y-coordinate on velocity. That means when you look at position, you're looking and saying, hey, what's the tangent slope at that same spot? And they have to match, because the velocity is the derivative of the position. Good question. 2 points. Anybody else? Cool. Oh, sorry, Cass, my bad.
I just, on 13, I'm just like, so when it switches from concave down to concave up, that makes the slope 0.
One second. Let me get something in front of us here. 1 second. Say again, Kat.
So, the dot at B is like, it's 0 on this. But that just doesn't make sense to me. I just thought it's.
You're okay, let's keep talking. So they're giving me a graph of F. And I'm supposed to figure out information about the second derivative. So what I'm really supposed to be finding is F double prime of A. This does relate to Hadley's question, so focus on this. What I notice is the graph of F is concave down right here. So all the y coordinates from whatever point this is to whatever point this is on the graph of F double prime, all of those y values will have to have negative y values. It's very much like what we did here. This section of the blue right here is concave down. And while the blue is concave down, all of the y coordinates on the F double prime function, those are all negative values. In fact, I can see that that's exactly when F double prime is negative. That's exactly when F is concave down. So here, I say at x equal a, the value of F double prime will be some negative number. It's good there. Then F is concave up. So F double prime at point C would have to be some positive number. B is the point of inflection on F. So if F is not, so at the point of inflection, we say that F is not concave up or concave down. It's switching. So if F is not concave up, F double prime can't be positive. If F is not concave down, F double prime can't be negative. There's only one possibility remaining. F double prime must be 0. Could be undefined, but that's less common. So F double prime of B has to be 0 because of the inflection point on F. So
Yeah.
2 points. Follow-up questions here. You want to have a different question they brought with them to class. Please.
21.
21, Tristan. Okay, y is a function such that y prime is always positive. So I would circle this on Danika's chart. Y prime is always positive. Y double prime is always negative. So that's here. Y double prime is always negative. Which of the following could be F? So if y prime is always positive, F must always be increasing. So the answer cannot be C, and the answer cannot be D. Questions? If F double prime is always negative, F must always be concave down. The only possibility is B. 2 points for Tristan. Anybody else? Follow-up questions here. Please, Rachel.
Well, it's not about this one, but can you go over 7 really fast?
You got some follow-up here. Okay, 7. Okay, it says which of the following graphs could represent the function whose slope is graphed here? So giving you f prime, you're trying to find the match to f. So this is f prime. One of these is f. So the first thing I notice is there are no y coordinates on f prime that are equal to 0. So that means there can be no places on f where the tangent slope is 0. So it can't be this one, because there's a place on f where the tangent slope is 0. So it's not that. Question? Let's see, I just go down Danika's chart. F prime is always positive. So f must always be increasing. So it can't be this one. Let's see. F prime isn't increasing. F prime isn't decreasing. So f prime can't have any concavity. So it's got to be this one.
Okay, yeah, that makes sense.
Video. Please.
So kind of like talking about not not number 32, but like the graph. So you said that like because it's so you know like velocity and acceleration and position, how there it's like f prime and f double prime. So for velocity, this graph, I guess I'm just asking, does it work both ways for the tangent slope? Like if I have a graph or a table of the position, can I say that like the y coordinates are going to be at those points on the velocity one, or is it just like from the okay? No.
You're doing just fine. Keep going.
So on here it's f prime because velocity is f prime. The graph or the table of f prime, when you put it into a graph on position, those y coordinates are where the slopes need to equal.
Mm-hmm.
Yeah. But is it the same for the position of it? Like if they were switched, like velocity and
Gotcha.
position, could you do that?
Gotcha. I think I have it. If I don't answer your question, keep talking about it. 2 points.
Or is it just one way?
One way.
Okay. And then it's one way from like acceleration to velocity.
Yes.
Okay. Not
So,
velocity.
So let me say it back to you. So if this said position, if this said velocity, I have to reverse the way I think. It would be a y coordinate here, but I wouldn't be able to see a tangent slope here very well. But a y coordinate on the velocity would represent a tangent slope on the position.
Can you do it like backwards?
Well, it's not exactly. It's actually the same thing. So slow down. So here's position, here's velocity, right? So this -1 is a y coordinate on the velocity graph. That's represented as a tangent slope on the position graph. You can't just switch it and say, well, if this is position, would this be a tangent slope on the velocity graph? No. Just one direction. But if this is acceleration and this is velocity, then that -1, the y coordinate on the acceleration graph, is a tangent slope on the velocity graph. Is that what you meant?
Yeah. If that was position, then that like 0 and -1, is there a way to tell what it would look like on the velocity? Go the other way.
Hold on a minute. No, because a y coordinate on the position doesn't really mean anything on the velocity graph at all. So that's a dead end. Yeah, that one point on the, I'm just searching, make sure I'm not forgetting something. That one point on the position graph doesn't really mean a whole lot on the velocity graph.
And then last thing, is there any like correlation if it was acceleration and then to position? Or would you have to kind of go through velocity and then from velocity to position? Or is there any like...
Gotcha. So the
crossover?
shortcut correlation is Danika's chart.
Okay.
But that correlation, so like for example, if I know, here's Danika's chart right here. If I know that I have a point on the acceleration, and that point has a positive value, then I'm certain that if I look at the position graph, where that point is, it would have to be a section of the position graph that is concave up. That you do know, but you don't have like a tangent slope connection.
Okay.
The tangent slope connection is from velocity to position, or from acceleration to velocity. Is that your question?
Yeah.
It's very good. 2 points. 2 more points. Anyone else come with a question? Cool. So we're just going to go with the blue now and do some examples from the blue to help with tonight's homework. sure. I don't remember if I giving you the symbol or not. So let's make sure you have it now. Okay, F double prime and this symbol here mean exactly the same thing. So you have to memorize that connection so that if you're taking the test and you see this symbol, you are immediately recognizing that, hey, that's F double prime. So make sure you have that memorized. Please, no.
Is it important to know why or not really?
Let me show you why, and then you don't really have to remember it. But knowing the why does make it a little bit easier to remember the symbol. So the function f sometimes gets equated with the symbol y. Is that fair? So when we take the derivative of f, one way to write that derivative is just f prime. But because derivative means slope, it's equivalent to saying let's find the change in the y value and divide that by the change in the x value. And the d really stands for infinitesimal difference. So the difference in y divided by the difference of x is the tangent slope. So that's where that symbol comes from. Good there? The next step is, well, what if we want to do it again? Like we want the derivative of this function. Well, that's why they just put another prime on it, like that. Make sense?
Yeah.
And then here what they do is they say, well, we need to find the change in this with respect to x again. So they do this. They do the d over dx of that, like so. Okay. Then they do something that's really goofy, I'll be honest. The d's are not multiplied. Okay, it's not d times d. But they write the final symbol as though it is d times d. So it becomes d squared. It isn't d squared. It's the second derivative. But that's where the symbol came from. That should be a y, sorry. And then they got dx times dx, which is like dx squared. Okay? But they said, well, it's not really squared, so who cares? We'll just write it like this. So the symbol to me doesn't make a whole lot of sense. But that's, I think, where it came from. So please forget all that. It's not that important. So it really isn't. As long as you remember what it is, it's good enough. So. Okay, back to here. They show us a graph of f. They say, in which of the following intervals are both things true? So you're looking along here, trying to identify when the first derivative is positive and when the second derivative is negative. So that's what I would do right there. This is the answer 1, 2, or 3. We'll ignore the combos. Work together so you can find the answer. Go. Looking for an interval where this first derivative is positive, which means it's an interval where the function is increasing, and an interval, and on the same interval, you want the second derivative to be negative and the function to be concave grounded. So feel free to work together. Vote when you have it. Or don't vote yet. We'll just kind of wait. I'll call for a vote in a second.
Yeah.
So that point is concave down, but it's also decreasing. So it'd be negative in the first derivative. Yeah, so just, good job.
That's too young. Increasing plus decreasing minus. So
Never, yeah, you're right.
tell me. No, then you try not to I like it. Just about like counselors, they're like, they won't say, what do you want to do? Like, I just want to do this. Well, you have to just do it. So, like, urging me to like shove it in the school. Like, I get it. I'm just doing my life. I'll do it. This is what I want. Like your concern. You're gonna overrush me your decision. You're welcome. I came up with that, and it didn't work for me. It worked for you. She told me to strike her.
Show me your vote. Show me. Show me your vote. Show me your vote. I'm going to give yourself 2 points. So F is increasing here. All along the red path, F is increasing. So all along the red path, the first derivative would be positive. All along the blue path, F is concave down, which means the second derivative would be negative. So the section of the graph of F where both things are true is right here, B to C. And you want more discussion on that. Cool, keep going. Okay, look at number 3. Okay, number 3 says a polynomial has a relative, okay, stop right there, polynomial. You do need to memorize the basic shape of all polynomials. So you've studied polynomials before, so quick review. Polynomials have these nice friendly shapes. Etc. Okay? So polynomials are always continuous. Polynomials are always differentiable. They're nice and smooth. They just have these kinds of shapes. Questions? Okay, using that as a clue, the problem says a polynomial has a relative max at -2, 4. So you have to have memorized that sheet I gave you that says a function has a relative max. Put this off. A function has a relative max when the function changes increase to decrease. So this polynomial has a relative max at -2, 4, which means, if I look at my picture here, at x equal -2 and y equal 4, there would be a point, and at that point, this graph of P would change from increase to decrease, causing a relative max. Questions? Cool? Keep reading. Let's see. The polynomial has a relative min at 1, 1, and another relative max at 5, 7. So I go back to here. Oh, I have a question for the whole room. I'll pay everybody. I just want to hear your votes. If you're yes or no, it doesn't matter. How many have had this experience before? You're working a math problem, and you start reading clues like this that talk about points on a graph, and you immediately think, well, I guess I need a graph, so you draw a grid. But then as you start plotting the grid, you start having trouble because you can't quite anticipate what the scale should be, like how far apart the points should be. And so as then like you scribble it out and you try again, and like just go like this if you've had that experience of getting frustrated by, yeah, 2 points for everybody. I have found the same frustration. So I came up with a solution to that frustration, and now I don't feel frustrated. On many, many problems on the AP test, I don't draw a grid. The frustration disappears. I just draw the points and label them. It's good enough. And then I don't get all messed up with like, what's the scale supposed to be, and just don't. Once in a while I'll do this, and then I'll say, oh, wait a minute, the scale might be helpful, but this is often enough. So 2, 4. Let's see, 1, 1 would be over this way and down a little bit. So see how precisely I found the location of that point? It's very precise. You can notice that, right? Okay. My sarcasm isn't very good. So this is 1, 1, and that's a relative min. And another 5, 7, is that right? So 5 would be to the right, 7 would be higher than 4. So again, precisely measuring. That's all I do. Question? Cool. So look back at the clue again. And no other critical points. So I remember the definition. A function has a critical point when the tangent slope of that function is 0. So this graph of P definitely has a critical point here, where the tangent slope is equal to 0, here again, and here again. But no other critical points. So that means as I draw the graph of P, I can't do this, because that would cause 2 more critical points. I don't have any option but to just go like this. There's no other choice. Question? Something like that. Question says, how many zeros does P have? 0 means a point on P where the y-coordinate will equal 0. Well, this y-coordinate's 1. So y-coordinate being 0 would be kind of here. So there has to be 2. Again, the point of this problem is not to memorize this. I will guarantee you with 100% accuracy, you will never see that question again. You'll never see anything even like it again. But what you will see are questions that make sure you know what zeros mean. You'll see questions that make you know that polynomials do this. You certainly see questions involving critical points, local min, local max.
So I get that those 3 aren't crossing it, so they're not really zeros. But if the tangent slope is 0, why isn't that creating 0? Or would that just be 0 on one of its derivatives?
Perfectly said, actually. Perfectly said. So this is P, and P has 1, 2 zeros, 2 places where the y-coordinate of P equals 0. P has 3 critical points, 3 places where the tangent slope of P is equal to 0. If we were to draw the graph of the derivative of P, P prime would have zeros at these spots.
Okay.
Is that what you said? It's perfect. 2 points. Next thing. So I'm going forward in the packet here a little bit. That one's okay. Should be okay there. Look at number 8, please. Well, please ignore this portion of the video as well, because that wasn't very helpful if you're watching the video and I'm standing there writing on the whiteboard, so sorry about that. You can hear me talking and never mind. Okay, it says the graph of f is shown in the figure above, has a vertical tangent at the point 2, 0. So right here, if we were to draw a tangent, the tangent would be straight up and down. That's what's meant by vertical tangent. And horizontal tangents at 1, -1, right there, and right there. Questions so far? It says, for what values of x between -2 and 4, by the way, when you see this, I don't ever say -2 is less than x is less than 4. To me, that doesn't convey any meaning at all. What conveys meaning quickly to my head is, oh, x is just between -2 and 4. So what values from -2 to 4 is f not differentiable? Okay, not differentiable means you can't find the tangent slope. So they want to know, along this path, at what x values can you not find a tangent slope? Well, right here for sure. Because when the tangent is vertical, we don't have any way of expressing what that tangent slope is. So I would say f is not differentiable at x = 2 for sure. Okay, memorize the following sequence of thoughts. Whenever they say, figure out when f is not differentiable, the first thing I'm looking for is discontinuity. If the function is discontinuous, you can't find a tangent slope at a discontinuity. So you can't find a tangent slope at a jump discontinuity, a point discontinuity, or a vertical asymptote. So here's some quick examples of those, way back here. Right here. Jump discontinuity, sorry, not jump, removable. So at the removable discontinuity, you cannot find the tangent slope. At the jump discontinuity, you cannot find the tangent slope. At a vertical asymptote discontinuity, you can't find the tangent slope. So first thing to look for when they say differentiable is continuity. Question. Okay, if the function's continuous, there are still two things that will cause the function to be not differentiable, meaning you can't find the tangent slope. Right here, the function is continuous, but at a corner, you can't find a tangent slope. And at a vertical tangent, the tangent slope is also not quantifiable, I guess would be the word. You can't quantify it. So 3 things. To be differentiable, you're looking at continuity first. If you see a discontinuity, then you can't find the tangent slope of the discontinuity. If the function is continuous and you see a corner, or as we saw in this problem, vertical tangent, you can't find the slope there either. So finishing this problem here, x = 2 is a vertical tangent. X = 0 is a jump discontinuity. No corners. Please, Danny.
Would 4 be like a vertical one or no? Because we don't know 100% for sure.
Can't say it better. It appears that if we kept drawing, it would become a vertical tangent. But because they didn't tell us that it was, we don't know for sure.
Okay.
Perfect.
What's the difference between a vertical tangent and an inflection point? Like from concavity?
Oh, this particular vertical tangent does occur at an inflection point, but they don't have to.
Okay.
Like here's an example of an inflection point right here, about right there, and that's not a vertical tangent. Does that make sense? Cool. 2 points. And you will be tested on that idea, like whether a function is differentiable or not. So we need follow-up questions to what you should be thinking when it says, hey, is this differentiable or not differentiable? Cool. Let's keep going.
Actually,
Oh, please. Right.
so if it said, is it differentiable from 0 to 2, does that work? I know it's not continuous, but I feel like is there still enough?
That's very good. You wouldn't include 0. You'd have to say, like, on the open interval, so right after 0, not including 0, and not including 2, the function would be differentiable on that open interval. Because everywhere along this path, I can find a tangent slope. I simply cannot find the tangent slope precisely at 0, nor can I find the tangent slope precisely at 2. But I can everywhere else. So the function would be differentiable on this path. 2 points. Anybody else? Cool. Here we go. I think 0. Well, we better go through this real quick. So look at number 10. Actually, 9 and 10. I want to make a comment on both of them. Move this out of the way. Okay, number 9 says the graph of a twice differentiable function. Okay, we just talked about how the word differentiable means you can find the tangent slope. And then Maya gave a really, really good example. She said, hey, look, right here along this path, I can find the tangent slope everywhere along that path. That means this function is differentiable along that path. I can find all those tangent slopes. This question says, here's a graph of f. And f is twice differentiable. So they're not showing you, so they're showing you f, and they're saying f is twice differentiable. Here's what they mean. All along this path, you can find a tangent slope. There's nothing that prevents you from finding each and every tangent. Point for the whole room. If I find all these tangent slopes and I make a list, raise your hand if you can tell me how long will the list be. Come on, hands. Don't overthink it. Just how long will the list be if I make a list of every single tangent slope that I find along here, Anna Kate?
I'll never end.
Never end. It'd be an infinitely long list. How many do that? Point. If I take all those dots and I plot them on a graph, I would see the graph of f prime. Does that make sense? So I plot f prime. If I then look at f prime, I would find that I could find the tangent slope everywhere along f prime. That's what twice differentiable means. I can plot every tangent slope of f, create a graph of f prime, plot every tangent slope of f prime, create a plot of f double prime. That's what twice differentiable means. Yes, please.
Could you theoretically just keep going? Like
With many functions, yes, but not all.
okay.
So like these functions here, theoretically I can go forever. It eventually becomes very uninteresting, but you can keep going. And so these functions are differentiable, twice differentiable. I can take the blue, and from the blue I can plot the orange. From the orange I can plot the red. Hence the blue is twice differentiable. Please, Elijah.
So what exactly does twice differential mean?
Simply means that you have a function. You can take and find the slope at every point on that function, and that would give you a plot of the derivative. And then you can do the same thing to the derivative, hence twice differentiable. Did that answer it? So they're not only continuous, f and f prime don't have any corners, and f and f prime don't have any vertical tangents either. That's perfect. So when they say that f is twice differentiable, that's a really good way to think of it. Since f is twice differentiable, you know that f is continuous, no corners, no vertical tangents. You also know the same is true about f prime. Well said.
So it just makes you can find the second derivative.
Mm-hmm.
Okay.
So they're giving you f, and they're just telling you, hey, it is totally possible to go find f prime. It is totally possible to go find f double prime. Okay, that clue, twice differentiable, that clue shows up in a lot of AP problems. Some of the times it's useful, sometimes it's not really useful. Like in this particular case, I'm not going to use that clue at all. Like I know I can find f, I know I can find f, so I know I can find f prime, I know I can find f double prime. Beyond that, I don't really need the clue. So, okay, down to here. I'll let you work on that on the homework. 76. Okay, it says which of the following statements is false? They were pretty friendly on this one. It says f is continuous at x equal a. Well, there's a removable discontinuity at x equal a, so f is not continuous. So that's the false statement. But I want to make sure you are comfortable with why the other ones are true. It says f has a relative max at a. The definition of relative max is function has a relative max when that function changes increase to decrease. I told you long ago, when you look at a graph, see points. So here's the points that I see. There's one right here. That wouldn't work right. Do that again. Come on. So there's a point right here. The very next point is the one up here. So from this point to this point, just say yes or no, did the function increase? Yes or no? Yes. Yeah. The next point is right here. Did the function decrease? Yes or no?
Yes.
Yes. That's why it's a relative max. So that's why this is a true statement. You want more explanation on that. The questioning today has been really, really good. I always joke that I know what questions are on the test. That's why I can tell when you're asking the right questions. So, cool. X equal a is in the domain of f. Okay, a function is just a list of x and y values, where every x has only one y, but we don't usually stress on that one right now. So I've got my list. Okay? If you find all the x's for which there is a known y value, then that's the domain. The domain is just the list of x values that have y values. So once know, is x equal a in the domain? So if I go to x equal a, I say, what's the y coordinate? Well, look at my graph. Oh, I can see it. The y coordinate is whatever that y coordinate happens to be. So I don't know what it is. Maybe it's 8. I don't know. So when x equals a, the y coordinate's 8. Therefore, x is definitely in the domain of f. Please.
So if it didn't have that like floating dot, then it wouldn't be in the domain.
Perfect. Perfect.
And it also wouldn't be relative maximum.
Perfect as well. Nicely done. 2 points. So here's what Brennan just said. It's too fun to not do it, so I have to do it. So we change this to white. We get rid of all this. Erase the axis too, apparently. So if the graph looks like that, then this is still false. F is still not continuous. But there's no relative max now. And x equal a is not in the domain. It's well said. It's very good. Anybody else?
It's just not in the domain because it's like not on.
Say it again, Danny. Say it.
It's just not in the domain just because it's undefined.
Perfect. Perfect. I can go to x equal a just fine. But because I do not find a known y coordinate, a is not part of the domain.
Oh, okay.
Would that make sense? Yeah. Perfect. 2 points. Anyone else? Awesome. The limit questions we've practiced, so I'll let you do that on your own. Okay. Do not do 13, please. So just skip 13. I don't really think it's worth stressing about 13 right now, so don't worry about 13. Let's go to, we'll come back to this one. 15. Keep going. On number 18, I would circle the word selected values. Remind yourself that when you look at a table, you're not seeing everything. That becomes very important for answering this question correctly. Keep going. Okay, let's go to 23. Okay, on the test, I believe there are 3 questions that will test your ability to understand the statement that is boxed right here. So I'll read the statement and then I'll talk about what the statement means. And then you just keep talking until you're perfectly clear as to what it, understanding it. It says if f prime is increasing, f prime is increasing. So what that really means is f is concave out. So if f prime is increasing, then as you look at the tangent and secant slopes of f. So if f is concave out, let's draw a picture. So here's f being concave out. F is concave out, and you look at tangent slopes of f. So you've helped me with this before, we'll do it again. Is this tangent positive or negative? Say it. Negative. Let's try again. Is this tangent positive or negative? Say it.
Negative.
Negative. Then we move along the curve point by point to a new spot. Is this tangent slope positive or negative? Negative. More or less negative? Less. Good. So from here to here, we see what we expect. F is concave up, so the tangent slopes are increasing. They're becoming less negative. I go to here, the tangent slope is 0. That's even less negative. If I go to here, the tangent slope is positive, and now more positive. Please, Dan.
So the f prime won't be positive until it is past the point where it's equal to 0, or is it on the positive on the other side as well?
So this is the graph of f, because the values of f prime are the tangent slopes. When f is decreasing, the values of f prime will all be negative.
Okay.
When f is increasing, the values of f prime will be positive. Perfect. And then the characteristic we're looking at, for Danny, is that when f is concave up, regardless of whether the values of f prime are positive or negative, those values do go up. Does that make sense?
Yeah. So just becoming less.
Right, perfect. So here's a picture of it, right here. Here's a section of, right here, the blue. So here's a section of f that is concave up. And while f is concave up, if we look at the values of f prime, which is the orange, we see values that are negative, less negative, 0, that's right there, and then positive, positive, positive.
Oh, okay.
So the values of f prime do increase, even though during part of it they're negative and part they're positive. But they are always increasing.
Okay.
Does that make sense?
Yeah, that makes sense.
2 more. So, back here, that's what this is saying. That when f is concave up, as you follow f, you see values of tangent slopes that increase. But the secant slopes do the same thing. So if I draw secants along here, like from here to here, okay, that secant is negative. The next secant is also negative, but it is less negative. So you see the exact same pattern whether you're looking at secant slopes or tangent slopes. That's what this box is saying. Question? Awesome. the pattern also works if you go from tangent, very negative, to secant, less negative, to tangent, even less negative. Okay, 3 questions on the test will probe to see if you understand that. Questions? So here's an example of that. Right here it says, we've got a function on the closed interval 2 to 5. The function has a positive first derivative. So f prime is positive. Negative second derivative. F double prime is negative. So Danika's chart over here for this particular problem would look like this. Let's see, the f prime is positive, so the function is going up. F double prime is negative, so the function is concave down. Questions? Cool. Which of these is f? Okay, I can immediately eliminate some of them. Raise your hand if you can see the ones that immediately do not match this requirement. Just raise your hand when you see it. So which of these functions don't meet one of these requirements? Like one of the requirements is really pretty easy to see. There we go. Which of those functions don't meet the requirements I've circled? Hands, please. Just want you to think with me. Let's go, Mikkel.
The ones that are decreasing.
So here the y-coordinates go down. Here the y-coordinates go down. Same thing. So none of these meet this requirement right there. Somebody knew it before I showed it? 2 points. Question. Question? Question? No?
No, I was going to say A1.
So,
That's not good about.
yes, no, you got it. I saw you got to that part. Yeah, it's absolutely true. It's absolutely true. The first one I looked at was just this, but you are absolutely correct. So over here, there's different ways to check it, but what I check is the following. With points, I can't find tangent slopes, but I can find secant slopes. Now, the method you're using, Weston, works just fine, but I would also make sense of what I do because it'll help you on some future stuff. So I'm going to find secant slopes. That means I have to find the change in x. Just say it. How much does x change? Say it. 1. How much does y change? 2. So that first secant slope is 1/2. No, sorry, 2 over 1. The next secant slope is 3 over 1. The next secant slope is 4 over 1. If the secant slopes are going up, the function is concave up. Okay? That's why B is the correct answer. The function is supposed to be concave down. Questions? Cool. I think you're pretty well. Yeah, please. Oh yeah,
Explain,
sorry.
like the secant, why it's secant slope with graph again.
So, just trying to make sure I understand your question. Is your question why the secant slope is 2, then 3, then 4?
No, I'm sorry. Why is the answer not A?
Oh, okay. So if I made a picture of this, I would see a graph where I'd see a secant slope that's equal to 2, and then then the next secant slope, like from this point to this point, the secant slope would be 2. Then from this point to this point, the secant slope would be 3. Well, that only happens if the curve is concave up. It's kind of like this section here. The slope from here to here, secant is from point to point, would be 2. Then from the next 2 points, the slope would become 3. That only happens if the curve is concave up because the chart reminds me of that. If the function is concave up, the tangents will increase, but so do the secants. So these are increasing secant slopes. It's concave up.
Wilson, please come to the counseling center. Chad will